it's a nice filter, you know? The gas Darth Vader.
Yes.
How does Darth Vader do?
I don't ever answer your questions.
I don't know, probably through a tube somewhere.
We got lucky with EV-131.
Huh?
We got lucky with 131.
Oh,
How it's had no midterm.
yeah, but we have quizzes then. And now we're running homework too.
Okay,
For the
guys,
last
I
quiz,
think we're
did
gonna
you have to
start.
use the Gaussian calculator for...
So, wait,
I remember we just had one part.
Yeah, I didn't use it. Well, I did use it, but not the whole one. Because I think it was like centered around.
I think so. It was very simple variance. Wait, okay, so this is you're going to do
Like the quiz was out.
Wait, what?
Oh, yeah,
I don't know if I want to check right now, maybe so. But what did you get for C?
Okay, ladies and gentlemen, we're going to be starting now.
For the C.
Hold on, before we even say anything, we are going to say something, okay? Hopefully all of you guys did your safety trainings and did your deposits, because we're going to be checking those really soon. And if you haven't done those, we're going to hunt you down and make sure that you do them, okay? So, yeah, hopefully all of you guys did them. I'm looking at you, Brian. And with that, this is an introduction to lecture 2, which will be on schematic design.
Okay, we'll start off with some quick updates. First off, lab 1, good job guys. I think every team got checked off, but there's still a lot of people who haven't because I guess like team communication problems. I mean, we've heard about a lot of them already. If there's more that we don't know or you haven't contacted us about, just let us know. Other than that, if you haven't been checked off, please come to us as soon as possible to get checked off, or we will reach out one by one, but that's kind of a pain for us. So it would help us a lot if you would tell us. But yeah, good job. We're going to review some of that stuff today just to make sure we're clear on that. Okay, 2 events that are going on. This is for IEEE, so we're going to... Well, actually, there's one more. Do you want to talk about the other one?
Oh, it's the other one.
The alumni thing.
Oh, yeah. Okay, so UCLA has this whole thing called the Alumni Mentorship Program, AMP, okay? And none of you guys are alumni yet, but you might want to be looking for someone to mentor you. So you should definitely apply to the Alumni Mentorship if you want to get mentored by an alumni of UCLA IEEE. I believe that the link for that was in the newsletter. If it wasn't, just let me know and I'll send you a link to it. So if you want to get mentored by someone who graduated from UCLA, that's the place to do it.
Sweet. Okay. On that, through a whole soldering workshop. That's held by our workshop leads. That will be this Thursday. It should be in the lab, if I'm not mistaken.
That being said, we're not going to use any through-hole parts, so yes. I'm not.
But it's soldering.
Yeah, it's soldering. Yeah.
You're gonna get. Wait, last year did they have like surface mount soldering?
No, they didn't have surface mount soldering.
Oh, surface mount. Okay. Well, it's still soldering. So if you don't know how to solder, you want to look at what it is. Then go there. Yeah. This one is the most important one, or at least that I feel, and I hope Alexi feels too.
No.
Come on, GB Info Night. Okay, this is Friday. Basically, a GB is a general board.
Yeah, it's called general board.
Okay, it sounds really scary, and I thought so too. But it's basically just like an ACA camp. Like it's just like a social group, I think.
Yeah. So pretty much it's going to be like 1 or 2 officers and like 4 or 5 students per officer, and pretty much it's like a cool group that you can hang out with because you know that we're all cool people, right? So yeah, you can sign up, come out here. Everyone makes cringy slides every single year, so if you want to just laugh at Tim and I.
Come on. We're both leading groups out there, but separate ones. But.
Yeah, we're separate groups. Mine's not as cringy as his.
Okay, that might be true. Basically, you're going to see all like the officers like leads and people who are going to have slides, and then you can choose which ones to like apply for. Basically, I think it's around 6 to probably like up to 8 or something. Like just members who are joining, and then you just like go out and get food or have small events or just like gatherings, you know. Very low down, unless your like leads are weird. But yeah, hopefully your leads aren't too weird and then just like easy. Okay. Last thing is team drive folders. So far we've been extremely unorganized, and we're gonna change that. So we have team drive folders that we'll send out to you guys individually, or not individually, but as groups. Let's already send them all up. So right now, in there, just like a blank bomb template that he has in there. So you're just going to replace that with your own. You can copy paste all your own stuff into there. And that's where you're going to have your bombs, your schematics, your PCB designs, literally any other material you want to use, just put in there so that you can share with your team, and it's an easy way. Because I mean, you know, we're still like pseudo virtual, so if you can't work on it together, that's an easy way to share it.
Yeah. And please name your stuff sensible stuff. I don't want to see any files named like final revision. Please name stuff like version 1, version 2, version 3. It makes it much easier for us.
Yes, I actually want to emphasize that. Just use V1, V2, like at the end of everything. No matter if you think it's perfect already, just add V1 to the end of it because you're going to change it.
Yeah.
That was a very easy way for us to figure out which one's the most recent.
Okay, and now that we have most of the boring stuff out of the way.
The boring stuff, GD is cool. Okay. Lecture overview. Today we will be starting on schematics. Yeah, we did EagleCAD last time, but that's like not a real schematic. So today we're going to be starting on real schematic design. Okay, you can kind of read this. Introduce a variety of components. That's what we're going to do today. We'll only talk about some of them, not all of them. Because next time, which is going to be like a couple weeks, we'll talk about the rest of them. So we'll get to all of them. We're going to help you out with choosing parts for bombs. I know we already did some of that, but this will help clarify some things, because I know we also had a lot of questions about that. Okay, a little bit of physics, and then at the end, Alexi will produce a high-tier demonstration of how to use our schematic program, our software, which is EagleCAD, that's what we're using, or just Eagle, I think that's what
Yeah.
So we'll go through these, yes.
Yeah, I'm going to show you how to create a project, how to schematic, basic commands. And by basic commands, I really just mean all the stuff you kind of really need to know. And then I'm going to talk about how to import libraries and where to find part libraries, because creating your own sucks. So it's much easier to take someone else's and use it in your project.
Yes, we love students. Okay, here's an overview. Well, we already said overview, but everything here that is underlined is what we're going to be talking about today. We already did motor drivers, so we're just moving from EagleCAD to EagleCAD. That's really, and we're going to review like how it works. I know some people are confused by that too. And then everything else here, we're going to go one by one. So this is the new stuff, and then the unhighlighted, or sorry, ununderlined stuff is just going to be what we're going to talk about next time. All of these are like sub-circuits of our overall board, so we're going to look at each of them individually.
Yeah, think of them like the liver, heart, and lungs.
Okay. What is a schematic? If you don't know what a schematic is, Todd's going to tell you everything that you need to know. Okay. It is a symbolic representation of a circuit. So like a circuit is a physical circuit, and it's just a simple symbolic representation. It's very standardized, so all the parts are going to look similar. Like, you know, resistor symbol is just like that squiggle. Right? Capacitors are 2 lines, so on. Okay. We don't need to worry about part placement because we're just worrying about connections in our schematic. So we just need to say this is connected to that, and then these parts exist. You don't need to worry about what the parts are actually like. Where they're placed or where the trays or how thick they are yet, we'll do that in PCB design. Yeah, so as it says here, we're going to show up, they're going to show up as electrical symbols and not the shape. So this is an example. This is a symbol. That is the footprint or the actual shape that will be seen on the board. Okay, a little bit of quick review over motor drivers. So once again, we talked about low side and high side. We're going to be using low side because high side is a waste.
Wait, hold on a second. Hold on. So let's ask a question for the audience. Why would we want to use a low side driver in this situation? There's probably 3 reasons.
If you can name one, we'll give you a smile.
Okay.
Yeah.
So if like when you turn it on, I mean like, well, I guess one reason is just so. Never mind, sorry.
Dude, don't worry. You got it. You got it.
No.
What are you thinking about? Maybe the idea can help generate some thoughts. Or yeah, sure.
So yes, that is true. We do like saving money, and for the same specs, essentially, an NMOS will most likely be cheaper than a PMOS by a couple of cents. But that's not the major reason.
Bigger picture.
Yeah, bigger picture.
But high side requires the use of an NMOS.
Yeah, the inverting level shifter. Yeah, so, well, the bigger problem is that even if we didn't have the inverting level shifter, we don't really have a good way of like controlling the PMOS because it's really annoying that you have to like pull it high for it to turn off. Whereas with an NMOS, we can just keep it at 0 for it to be off. But yes, you are correct. Is there one more reason?
A couple, yeah.
Yeah, there are a couple more
Any
reasons.
other ideas?
Yeah.
Well, I mean, I'll go off of what Jenna said and just say that yes, they're cheaper, but because there's more components, like, as you said as well. With the inverting level shifter, we can spend less money on a larger scale. Yeah. Less than 4.
The other thing that I want to add is that the motor is not a sensitive electronic component, so it doesn't matter that it's not directly connected to ground, so we can get away with doing this, because if you add something like a op amp right here, which if you guys don't know what that is, stay tuned for EE11L, you guys are going to use those there. You want that to be connected directly to ground because it uses ground as a reference. A motor doesn't care about any ground references. All it cares is that current is flowing through it, and that's why we can get away with this.
Okay. I guess just general overview. Okay, yeah, sure. I'll run through really quickly. Okay, we have a PWM signal going into our gate of our NMOS. Our NMOS source is connected to ground. We have a pull-down resistor from gate to ground, and then our drain is connected to the rest of the circuit with the motor, and then the diode in reverse bias. And
Oh, hold on a second. Well, why do we have this here? This is a question to the audience.
You look very confident. You want to say?
To remove.
Get rid of any excess charge in the gate.
That is correct. It pretty much makes sure that this pin, when there's no PWM signal, is grounded, and it allows you to bleed off excess charge from the gate that might have accumulated there during regular operation, yes. What about this diode? Why is that here?
Protects back EMF.
Okay, yes, because remember when we switch there's current flowing through the motor, we switch this off, it's going to generate a back EMF, which will, because the motor is an inductor and wants to sustain current. Generally speaking, you have high potential here, low here, so there's no current flowing through the diode in regular operation. When you have a back EMF, you have positive here and negative here, so you have current flowing in this direction and can flow through the diode. Otherwise, you'd have a problem because current would have nowhere to flow. So yeah, that's pretty much it, I think, for this.
And a note about high-side drivers. We went over high-side drivers. I think during checkoffs, we found that a lot of groups were confused by how inverting level shifters work. Well, you can forget about that because they're not using it.
Yeah.
It's a good teaching point.
Yes, it's good.
Other than that, we're not using it.
Yeah, and it's also good practice for you guys to work on your bomb skills because we're never going to use it. So even if you made a mistake, it's okay. Because,
Nice.
Yeah.
I think we talk. Okay, yeah, we do talk a little bit more about having a true ground here. Okay.
Yeah.
So these are, as Alexa was saying, these are the reasons why we want to use low side driver. First off, you don't need the inverting level shifter, which means cheaper and less complicated. And second, about the true ground idea, which is that our motor's negative terminals right here are connected to the NMOS drain rather than the actual ground, which, as he said, it doesn't matter in our case. And I think he also touched on it last lecture when he said that the benefit of using a high side driver is that you are connecting that part to a true ground, which in our case we don't need, so we're going to use a simpler and cheaper version. Okay, so what is this for? Oh, right, okay. Specs for parts. You already went through this, but you might want to go over it again in case you find something here. Well, we didn't check your bombs yet, so we will be checking that very soon.
Oh, we didn't check them very carefully.
We did check very carefully. We looked over it, but we're going to go into each individual link and see to make sure. But these are some additional specs if you haven't considered them in the past. So first off, for our transistors, we want them to be able to hold enough current to spin our motors at an adequate speed. So that was, we are considering overhead, right, 5 amps for us. So we already consider having a little bit extra. So 5 amps is what you're looking for. Anything above 5 amps works. Gate source threshold. So we talked about threshold voltage a little bit, having the difference between gate and source being greater than the threshold means the MOSFET is on. We want that to be as low as possible, so this is about 1.5 here, which is fine.
Yeah, so our GPIO signal is 3.3 volts, so this is less than half of that, so it's definitely going to hopefully work.
Yes. This is a suggestion for footprints. They come in SOT, so SOT 23 is similar. You'll see a lot of options for those. I'm sure there's plenty. And okay, yes, in stock. Because I saw with Alexi that a lot of stuff that you guys put. It should be on the very top right. It'll show very big letters and bolded, not available, or like 0 in stock. And there's also some stuff that you can only buy in packages of 10,000 or greater. So we only want a couple of them, so we don't need that either.
Yeah.
And if there's 2 choices and one of them's less money, it helps save the club money because we're not spending any of our money. Nice. Okay, so we're gonna start on the actual like topics that we want to talk about today. There's not that many, so we'll try and get through fast. Decoupling caps. Okay, if you work with capacitors in the past, you know that they're commonly used as decoupling, and this word basically just meaning that they're helping us reduce noise. So every voltage source has some kind of noise, like the signals aren't pure. They have some kind of oscillation, around the ideal level, but with the capacitor, it will reduce that variation. So, right, our main goal is to suppress noise. This is like a side effect. It can act as a if you think of like capacitor as being able to contain charge, and then it can kind of release that charge when it's necessary. So when there's voltage dips, it'll help supply extra. This is kind of an example of this bottom one. On the left, on the left is a voltage source without a capacitor. On the right is with the decoupling capacitor, and you can kind of see the oscillations are a lot smaller in amplitude. So that's what we mean by reduced noise. Yeah.
So if the next slide doesn't cover it, I want to go back a slide actually. So I'm going to quickly introduce you to a little bit of physics. If you've taken AE3 here, you definitely know what impedance is. Pretty much impedance of a capacitor is 1 over j omega c, right?
Yeah.
So yeah, good thing I know my stuff, right? So what that pretty much what this value means, you can think of impedance as complex resistance. Like with a resistor, you have Ohm's law, V is equal to IR, right? That's pretty simple. With impedance, you make it V is equal to IZ. That means that the drop in potential is proportional to the impedance of the part that you're looking at. So for a capacitor, what the impedance is, so impedance is a function of frequency, because remember it's 1 over j omega c, omega is angular frequency. That means for certain frequencies, your impedance is going to be higher or lower than for other frequencies. Specifically with decoupling capacitors, the way it works is that for higher frequencies, your impedance goes down, which means that for higher frequency, you have a path that goes to ground. Whereas for lower frequencies, such as DC signals, that's a really low frequency, the impedance is infinite, so it doesn't go down through the capacitor, it goes along this way. The other way to think of it is, you know how a capacitor stores charge, right? If there's ever, and it likes to maintain the same voltage, by the way, that's another thing capacitors like to do. But let's say you have a signal that has a slight bump up, right? It passes the capacitor, it's going to go onto the capacitor, like that's a bad way of thinking it, but you can think of this sort of as a reservoir. Any excess goes to the capacitor. Then you have a dip down. As the dip passes, the capacitor is essentially going to raise it up a bit, and it'll
using the excess reservoir.
Yeah, using the charge that's stored in the capacitor. Now that's a very bad way of thinking about it. The better way is obviously to think of it with impedance. That being said, I think this way is more intuitive, where this is essentially works as a reservoir and can like give a little or take a little depending on what's going on here. And the next slide now. Unless there are other questions. Yes.
Yeah.
Can impedance be thought of as resistance?
It is
Similar idea.
it is similar idea. The difference is that it's now a function of frequency. Like the impedance of a capacitor is just its resistance. The difference now is that you're no longer looking at it as a function of, like you're no longer looking at it as direct current, it's alternating current, or alternating voltage, depending on how you want to define
The
it.
same idea that is like limiting current.
Yes.
Yeah.
So are we gonna like add a resistor, or are we gonna like short basically across the capacitor?
No, we're not. The impedance is an intrinsic part of the capacitor. Like the impedance of a capacitor is 1 over j omega c. So it will actually, I think your question is like, how does current get from here to here, essentially?
No, like, because like it might like, because we're just connecting it like without any resistance, it might.
It won't short because this isn't open, right? These two plates are not connected in any way. So you don't need to worry about there being a resistance. Yes?
What's J?
J is the imaginary number I. So in physics, you call it I. In electrical engineering, you call it J. Yeah.
And also, I think he mentioned earlier, just to clarify, Z is impedance, the symbol for impedance.
Yes. And just for the record, in order to do the schematic, you do not need to understand what impedance
Fun
is.
fact, yes, this is fun fact.
Yeah, fun fact, all you need to do is follow our directions.
All you need to do is click and drag symbols.
Yes.
It's very great, fun fact.
Yeah, fun facts, okay.
Okay, right, so ideally capacitors are just pure capacitance, which helps us filter out noise, but they do have some parasitic effects that are inductance and resistance, which we don't want. So what do we do? Well, if we put them in parallel, you can see these three basic laws here. But basically, if you put capacitors in parallel, they add the capacitance, which is more of what we want, and then they diminish the resistance and the inductance, which is what we don't want. So increasing capacitance, decreasing inductance and resistance. So that's why a lot of times in our circuits, we'll have more than one capacitor, but they're not in series, they're in parallel.
Yes, that's the other thing, if you guys know your circuit theory, putting capacitors in series reduces their capacitance, which very often you do not want, because at that point you should just use a capacitor with a smaller capacitance.
Okay, this is a little bit more physics. PCB traces have some resistance and some inductance. We won't care about this in schematic, as we mentioned. We only care about what connections there are. But in the actual design, we're going to determine where do the traces go, and how thick they are, how long they are, stuff like that. That's going to matter in PCB design. So we'll talk about this now, and then you're going to apply it later. But this is good to keep in mind for now as well. Yes, okay, so we have two graphs here, or two diagrams. Ideal decoupling capacitors will have the impedance shown in the top right one. This is a constant slope of negative 20 decibels
Per decade.
per decade, okay. And you can see, okay, I can't even read it here. But basically, it acts kind of like a high pass filter. Okay.
Oh, it acts like a low pass filter.
Acts like a low pass. Acts like a low pass. It's filtering out high frequencies. That's all I'm saying. Acts like a low pass filter. Okay. Well, once again, as we said, these are not. These are ideal and they're not real world capacitors. So real world decoupling capacitors have what is in B. Basically, yes, there is that red portion of that graph you see, but there's also that green. And what that green is indicating is the inductance. And you can also see that the graph shifted up because of the resistance. So as we said, right, resistance and inductance are what we're considering here. So you take the first one, copy it down, and then you add that green, and then shift it up. That's what we have for real life. You can kind of see that this is now a band stop filter. Sorry. Because it's a low pass filter and then a high pass filter combined from the inductance and the capacitance that creates a band stop. If you're not familiar with these terms, I don't think that's necessary. So.
Yeah, it's not necessarily a problem to know what a band stop is, but you can look at the shape. It doesn't filter out frequencies here. It doesn't filter out frequencies here. It filters out frequencies in the middle. That's the stop band, because those frequencies are stopped from passing. Yes. So.
Okay, yes, okay, so this helps us as well. So basically, when we have multiple decoupling capacitors, it will help us filter out more noise. So this is all filtering out noise, that's what we're trying to do, right? And we have a band stop filter, we're filtering out a certain frequency of noise. When we have multiple capacitors, as shown here, they can combine into this red line that we see. And that's the net from the net filtering from our parallel combination. And you can see that there's more, like a thicker band that we're filtering out, which is good because we want less noise and less of that central section is going to be there.
Very nice.
Okay, yes, smaller capacitances in general will filter out higher frequency noise, and the larger capacitances will filter out lower frequency noise. So this is a chart showing what that means. We will be given, or all of you guys will be given the decoupling capacitor values. That's going to require some data sheet reading, and we'll also give some to you guys, but a lot of it's going to be like, oh, for this specific part, like for instance, for a voltage regulator, there's going to be some decoupling capacitors, or at least in my experience there were. So you're going to need to find, okay, what decoupling capacitors do I need, and then just put them in, okay? I'm not sure what this is. Is this for DMC?
I believe that this was a reference to the microcontroller, or it might have been a reference to the voltage regulator that I was going to demo at the end. I'm not quite certain because I
don't mind about this one. Basically, the idea is you're going to be like searching through a pile inside the data sheet. The data sheets are very long, but there's always like certain sections that are way more important than the other ones, and that's what are relevant to us. So, knowledge concerned, yeah. Basically, you will find out what values to be given, so you won't have to guess.
Yep.
I have a question.
Oh, yeah.
Oh,
Where does the noise come from?
so the noise comes from okay, so you know, it comes from everywhere, just for the record. Literally the fact that heat exists in this room means that your electrical circuit has noise in it. I believe it's called Johnson noise. I'm not 100% sure if that's the correct name. Your voltage regulator creates noise. The way the voltage regulator works, I'm going to talk about in a later slide. Well, some of them just pretty much drop the potential across the load. The ones we're using are called switching voltage regulators, and they just switch on and off at a high frequency, and in conjunction with an inductor, they can create like a steady output. The problem is if you're switching at 2.5 megahertz, you're guaranteed to have some noise pretty much at 2.5 megahertz on the output. The other thing is your microcontroller. It works at 100 megahertz, let's say for an example. That means that the stuff inside of the microcontroller is switching at 100 megahertz. If something is switching on, it causes a small dip in current because it requires current to operate. If something is switching off, all of a sudden you have a bit of excess current. Pretty much any time the state of a circuit changes, something turns on or off, you're going to get noise. Then you also have random noise from electromagnetic interference, as well as just heat, which causes electrons to move either faster or slower depending on the part, or just to randomly hop over from one place to another. So noise comes from everywhere. You can't avoid it. Does that answer your question?
Yeah.
Okay.
Okay, before we move on, these are more specs, and these are for capacitors in specific. So capacitors, obviously, that's what you need to consider. That's the most important thing. If you guys have been using DigiKey, there's always an option for the actual value. Then there's an option for package size, and then there's an option for footprint, like SMD or through. Just to repeat, we are using all SMD parts, so that is most important. So select SMD, select your value, and then your package size, if you know what it is. Okay, type, oh yeah, okay. So if you're using a DigiKey, there's a bunch of different options for capacitors. We're using ceramic. So that should be the first one, I think. Voltage rating, these values, voltage rating, ceramic, yeah.
So voltage rating means pretty much anything above this, you run the risk of ruining the capacitor. I'm pretty sure the lowest voltage rating you can find is 6.3 volts, which is fine. Just try to use 6.3 or above. There might be something that's like rated at 2.5 volts for some reason. I don't know what the reason is.
Well, again, we're at 3.3 or 3.7, so.
Yeah.
I mean, we can just use like 5 or 6. Oh yeah, you can just say 6.3 is your minimum. So there's no precision. Okay, so these ones in red you don't have to worry about. That's what it is.
Yeah, precision we don't really care about. ESR we don't care about. ESL we also don't really care about because we're not working
First
with.
three.
Yeah.
And package size and service mount.
Yeah, we care about that. So I'm going to talk to you guys about the battery and voltage divider. So you guys know what a voltage divider is, right? Yeah, okay, I see a thumbs up. Okay, I don't see anyone shaking their head, so I'm going to assume that you guys know what a voltage divider is. But just in case you don't, it's two resistors in series, and we take the voltage at the middle point, and it's going to be a fraction of the voltage across both of the resistors, and it's going to depend on the ratio between the two resistors. Now you might be wondering, why do we need this? Well, the thing is, we're using a battery. The thing about batteries is that they lose charge. The thing is, when they lose charge, they also experience a shift in potential. For a LiPo battery, I think I have a graph of this on the next slide. It starts off at roughly 4.2 volts, then it goes to 3.7, it plateaus at 3.7 for a while, and then at the very end it drops off to like 2 volts or something, really low. The purpose of this circuit is that with our microcontroller, we can sense voltages from 0 to 3.3 volts. The battery starts off like roughly 4.0, so if we just directly connect the battery to one of the pins to measure the voltage, we're going to risk damaging the microcontroller. What we can do with the voltage divider is we can step down the voltage, because voltage here is going to be a fraction of the voltage here, to a safe level, and then we can measure that level, and once we detect it's below a certain threshold, we can say, okay, the battery's discharged, I'm not going to fly the drone anymore. And this is pretty much a way for us to easily check the level of the battery.
And FYI, I think for our values, we're just looking for R1 and R2 to both do 10K.
10K, okay, 10K is reasonable. Here's the other thing, okay? You asked about noise, right? You might think, I'm going to make this 1,000,000 ohms, and I'm going to make this 1,000,000 ohms, because that way no current's going to flow through here, I'm not going to waste any energy, right? Because you just made this like 1 ohm and 1 ohm, a lot of current's going to go through here, you're going to waste a lot of energy. If you make this 1 million and you make this 1 million, you're going to have a lot of noise on your output because, as a matter of fact, I think you're going to suffer from the fact that there's too little current flowing through here, and that the fluctuations in the current are going to be more evident here because there isn't enough of it. If you have a lot of current, it sort of like averages everything out. If you have like, you're not just going to have like a single electron at a time flowing, but let's just say, for example, you have a single electron at a time flowing. There's going to be much more variability here just because it doesn't average over such a large number, which is why we recommend you stick to 10K. Right, so this is what I talked about. It starts off at 4.2, drops off to 3.0. So I lied when I said it was 2.0. But pretty much this is what we're going to be trying to measure with the voltage divider in order to make sure that we ideally don't go past this point, because the problem with LiPo batteries is that if you discharge them too far, you risk damaging them. If you damage them, they're going to perform worse, and you don't want that.
And an additional note real quick is that we don't want that in particular for our drones, because imagine our batteries operating at a lower voltage than we expect, and then it starts slowly drifting away. And like, okay, basically we're operating at a voltage that we don't expect it to be in that time.
Yes, and you had a question.
What are the different colors?
Right, so the different colors, I almost forgot to talk about this. They correspond to different C ratings. The C, so this is 0.2, 0.5, 1.0, and 2.0. The C rating is the rate, so you have it's the rate at which you can discharge the battery, essentially. So higher C ratings mean you can discharge it at a faster rate. I believe that the way you determine the rate at which you can discharge the battery is you take the capacity, and then you multiply it by the C rating. So if you have like a 500 milliamp hour battery and you have a C rating of 2.
I think we're going to be using 25.
Yeah, I know we're going to be using 25, but I don't know how to do math in my head. So if we have a C rating of 2, that means that you're going to be able to discharge it at a max of 1 amp. Because you multiply the current capacity by the C rating to get the current that it can output continuously. So as you can see, with higher current ratings, the voltage curve does go down.
Actually, fun fact. Last year, our leads gave us batteries that outputted at around, I think, 500 milliamps, as he was saying. But the C rating was 1, so the basically like net, after considering the C rating, current output was 500 milliamps, or just 0.5 amps, which is not even close to getting our drones to lift. So basically, at a certain point, when you run a high enough duty cycle, the motors would just turn off. And then every team was wondering why the heck that happened. Turns out they messed up. But hopefully we won't do that this year. Basically, you have to buy your own batteries and then redo the whole thing.
Yeah, so we
This time we'll consider that. Yeah. Learn from mistakes.
Yeah. So here's a slide which you don't need to worry about, but you will in the future. Voltage divider, so you remember how like you can think of a PWM signal as an analog signal when it's not really, because like the time average value corresponds to an analog value. Well, with the voltage divider, you don't get this luxury. So you're going to need to connect it to one of the pins here on the, well, ignore this. I don't know why I even included this table here, because I think we're going to be using a different microcontroller anyways. Pretty much, the point I want to make here is make sure to label that with a reasonable label on your voltage divider. So your label will go right here, by the way. Make sure to label it something reasonable, and just keep in mind that you need to connect it to a pin that is actually capable of sensing an analog input. That being said, this is just a warning for the future.
Oh wait, okay, 2 things. 1, labels are how you label traces on your schematic, and Alex is going to show that.
It's actually labeling wires.
Oh, labeling wires, sorry. Okay. And second thing, this, even though this chart isn't what we're going to be having, this is like the same exact thing that it looks like with our microcontroller on the data sheet.
Yeah, so this is like a sample from a data sheet, so if you're scared now, like, I don't know what to say. It's Halloween, okay? So, yeah. The other thing that I want to talk about, the other like big source of noise in our circuit, and the reason we include it. So a voltage regulator, like the name implies, is to regulate the voltage. So like let's say you have 5 volts at the input, but you only want 3.3 volts at the output. You could use a resistor if you had a constant load, but with like a microcontroller, you can't guarantee that it's going to be a constant load. Or like let's say you have motors which might drop the voltage on the input down. So a voltage regulator is an active component. What it does is it regulates the voltage. It can bring it down and can adjust it. So like, let's say your input voltage changes from 5 to 4 volts. The output is still going to stay at 3.3 because this thing is smart enough to compensate for that change, unlike a simple resistor. What we want is our battery is 3.7 volts most of the time. We want it to output a voltage of 3.3 volts all of the time. 3.3 volts is what's going to go into our microcontroller radio and IMU. IMU is inertial measurement unit. You don't really need to worry about radio and IMU yet. So there's two types of voltage regulators that are kind of big. The first kind is the linear voltage regulator, the second kind is switching voltage regulators. So I alluded to linear voltage regulators earlier when I answered Josh's question. What they do is they drop potential across a resistor, but they can vary the resistance such that the amount of potential that is dropped makes it such that the output is constant. So they have like a nifty trick going on in the middle. I believe they use an op-amp as well. That being said, I can't be 100% sure. And you don't need to care about them because we're not going to be using them. The reason that we're not going to be using them is because they can't raise a voltage, they can only drop it. The other problem is that they are not really efficient because a resistor dissipates heat. That heat is energy that you could have used for something else. That being said, they're really nice because they're really simple, really cheap, and they have low noise on the output. The reason they have low noise on the output is because there's no switching inside them. It's just dropping voltage across the resistor. Switching voltage regulators, though, are what we are going to be using. Pretty much, it uses switches to switch the output on and off to produce specific output voltage. It's not quite the same as PWM because it uses energy storage elements, typically an inductor, to make sure that the output is constant and not like a square wave. That being said, they suck because they have noisy output with noise dependent on the duty cycle of the regulator. So if you have 2.5 megahertz duty cycle, you're going to have some noise at 2.5 megahertz. They also usually require more external components, such as an inductor. That being said, they can produce higher output voltage than input voltage, so they can raise it, which is something that you can't do when you're just dropping potential across the resistor. The other thing is they're really high efficiency because they don't use a resistor again, and inductor stores energy instead of dissipating it, which means that they don't waste energy.
To confirm in your sample applications for voltage regulators, a common thing is to see at least one inductor and a lot of decoupling caps.
Yes. That being said, for switching regulators, there are 3 types of switching regulators that you need to worry about. Or actually, you only need to worry about one. You need to worry about avoiding the other 2. The first type is a buck regulator. A buck regulator works pretty much just like a linear regulator in that it takes a high output voltage, high input voltage, and gives a low output voltage. So going from 5 volts to 3 volts is possible with this thing. Going from like 1 volt to 3 volts is impossible. The other type is a boost regulator. What it does is the opposite of that. It takes a low input voltage and raises it to a high output voltage. So you might have 1 volt on the input and 3 volts on the output. They do this through a combination of magic and analog circuits. The one that we want to use is a buck boost regulator. The reason for this is because it combines the benefits of a buck regulator and the benefits of a boost regulator. And I'm not sure if I talked about this in the next slide, so I'm going to take a peek. Yes, so okay, so yes I do. So you might be saying, wait, our battery's 3.7 volts, right? And like towards the end it dips down, but we're going to stop our quadcopter before that. Why can't I just use a buck regulator? Like, that's a reasonable question. The reason for this is that the battery has a certain internal resistance. This is another thing I think that they cover in EE3. Pretty much what this means is that a perfect battery would just be a voltage source. Ours is a voltage source in series with a resistor. Under high current draws, such as our motors being at full consumption, this means that there's going to be a drop in potential across the internal resistance of the battery. So the output isn't guaranteed to always be above 3.3 volts. At max current consumption, for example, it might drop to like down 3 or 2.5 volts. I don't know, I didn't really ever measure this. All I know is that it goes below 3.3 volts, and you can't get away with a simple buck regulator. That's where the boost comes in. The boost takes over the moment the input voltage drops within 3.3 volts and raises it up to 3.3 volts again. That's the reason we need it. And over here, I just include this graph again. Like towards the end as well, like you need a boost regulator in order for the microcontroller to work correctly. Right. So now, for choosing this part, you might say this is a tough part to choose, and you would be correct. So we forced some minimum specs upon you. You must use the buck boost topology for reasons explained previously. The input voltage must range from 2.3 to 5.5 volts. You can go above 5.5 volts, but in my experience, the majority of small regulators have a max ceiling of 5.5 volts, which is more than enough for us. Output voltage has to be 3.3 volts because our parts operate at 3.3 volts. Output current has to be at least 300 milliamps because the combined current consumption of all of our digital logic is like 200 milliamps. So this gives us a safe margin. I also listed a few good companies, Texas Instruments and Analog Devices. They both have huge portfolios of parts that you can pick from for these regulators which satisfy these requirements. Other things to look out for, make sure it's in stock. Don't be an Alexi, okay? In September, I ordered parts from Mauser thinking that they were going to come on September 19th, 2021. I was lied to. They were going to come on September 19th, 2022, okay? So you have to make sure these things are in stock. They have like 77-week factory lead time. It's ridiculous. So please make sure that they're in stock. By the way, Analog Devices has more stuff in stock than Texas Instruments, so that's the thing. Make sure you're using the correct variant. Most regulators have 3 or 4 different variants. Adjustable, 5 volts, 3.3, and 1.8. Make sure you're using the 3.3 one. If you use the 5 volt one, it's going to fry your circuit. If you're using the adjustable one, you can use the adjustable one, but it's just an extra hassle of setting up the voltage divider for it. And the 1.8 volt one is a bit too low for what you want to do. So for example, the TPS 63001, which is the one I tried to order here, is perfect, except you can't buy it anywhere right now, which is why I'm using it as an example. It matches all of the specifications out there. I believe it's capable of outputting 2 amps, which is overkill, but you know, it's good enough. It's out of stock. You can't buy it. It's not suitable. We're not going to let you use it. It's literally out of stock everywhere, by the way. That being said, you might go on DigiKey and notice that the TPS 63000 by Texas Instruments seems very similar to the TPS 63001. And it's in stock. There's like 60,000 of them in stock right now. That being said, it is a variable output voltage regulator, so you can't just use it in place of the TPS 63001 and expect it to work. A team last year thought that they could get away with this. They couldn't. I believe their output voltage is like 0.2 volts. So they had to go and find the TPS 63001 somewhere, and when they soldered it, worked. But just be careful, watch out for this. Sometimes in the application schematic, it might look like the circuit that you're trying to build for yours works, but you really just have to check that the variant you're using is the fixed output version at the correct voltage.
Okay, 2 notes. 1, if you're using something from bigger companies that's more well documented here, it's going to be a lot easier for you to find like a footprint or a symbol online. So that helps a lot. So you don't need to scan through like 300 pages. It should be a good option within the first couple. 2, just a heads up, soldering these are a complete pain. In my experience, it was like a leap of faith because there's pins on the bottom of the board where you literally can't see. So you just pray that you're doing it right, and if it doesn't, it blows up.
It doesn't blow up.
It doesn't blow up. It will just not smell good.
No, it doesn't even not smell
Dude,
good.
I have to take my
Okay.
Some weird stuff is a leap of faith. Yeah, that's just what I said.
Yeah, it is a leap of faith. I'm also going to briefly talk about the radio and IMU. You guys do not need to worry about how these work at all. What you need to do is pretty much break out the pins for these. The radio has 8 pins: ground, VCC, CE, CSN, SCK, MOSI, MISO, and IRQ. Pretty much what we're asking you to do is to connect a label to these pins in your schematic with a reasonable name. So, for example, the MOSI pin should not be named what is this? It should be named MOSI _ NRF24, or something like that, okay? A reasonable name, please.
We're going to talk more about these next week, by the way.
Not next week,
Oh,
next lecture.
Next lecture, sorry.
Yeah. Same thing goes for the IMU. By the way, we're going to give you a library with all of these parts, so don't worry about that. What you have is pretty much the same thing. You have VCC, ground, serial clock, serial data. We don't care about the last 4 pins, but they're auxiliary serial data, auxiliary serial clock, I2C address select, and interrupt. We won't be worried about these, but what we are going to ask you to do is just add labels to these. That being said, we're also going to have a request for you to put a couple of decoupling capacitors in front of these. And that's going to be part of the lab where we specify which values we want at which pins.
As another heads up, something that I was confused about was, coming in, I wasn't certain how these were going to be connected. These are breakout boards, meaning they have boards of their own, and we bought them. How we're going to connect them are, there's going to be header pins. They're basically just like literal pins that will stick into these, and then we're going to connect to our board like that. They're going to sit on top of it. So everything else is going to be soldered on. Like there's very thin components that are being soldered on our actual board. This is going to sit on top. So it's going to be up here, and it's going to be connected through these like other external pins.
Yes, what a brilliant explanation. You're pretty much going to have a sandwich, and there's going to be 2 layers. Right, so questions. And by the way, please stick around. Just because it says questions doesn't mean it's the end of the presentation, because I want to give you guys a live demonstration of Eagle, which I never got, and I was super confused, and I tried to do it myself.
We have a link to a tutorial in the lab, but it's definitely not as great as our very own appendix.
Yeah, you guys are going to have my own unfiltered opinion of what EagleCAD really is.
Might get a little bit PG.
Right, any questions? Okay.
Actually, I think we have one slide after this.
Oh, we have a slide after this?
Yeah, this one. Okay.
Oh.
Actually, I'll probably just do this for every lecture from now on, because I think it's helpful. If you guys are looking for like, what the hell do I do? I'll just add a slide at the end for everything, so that you know what you have to do, okay? 1, if you haven't checked off, we will tell you. 2, team drive folders, we're going to send out links. Put everything you have in there that you're working with. We don't need your EagleCAD links, those are useless. We just want your bombs and your schematic designs. You don't need to do like, oh, every time you upload, because that's not how it works. Your schematics are not like Google Drive where you can share and like work on it at the same time. It's going to be, you develop it on your computer, you upload the file to Google Drive, and then we'll be able to see it. So you don't have to do it at every step. Just after you're, I think honestly, just after you're finished with it and we're trying to look for checkoffs and stuff, upload that final version, okay? Okay, events, right? These 2 events, through-hole soldering. Yeah, sure, it's cool. GB nut, go there. That sounds fun. Okay. And then our lab, a little bit of overview. You're going to be implementing all of the circuits that we talked about today, but as we said for radio 9U, very simple. It's literally just like slap on some labels.
Yeah.
And then the other ones are also honestly not that difficult. You just have to read a little bit of data sheets. Most important parts, not forget, we bolded in the lab. Add the parts that you use to your bombs. Everything that you need to use, you need to pull on your bombs. We split it up by section, so each sub-circuit, so you'll be able to see that. And also, one thing that I didn't do when I took AP was read through the lab. So I was really confused. Read through the lab, basically. It will help you not be as confused if you have any questions. Yes?
When is the soldering workshop? Like
Oh.
what time?
It's in the evening. I believe it is from 6 to 8.
Check. If you're in the newsletter, it'll be there.
It is definitely from 6 to 8 because it got rescheduled because it was overlapping with the town hall, which was also from 6 to 8. So it's going to be in the IEEE lab, which is Bolter 2825 from 6 to 8 p.m. on October 28th.
If you look on Instagram, it'll say there. If you look on the Facebook group, it'll say there. If you look on email, it'll say there.
Yes. Okay. Any questions, or can I get cracking with Eagle? Okay, I got a thumbs up.
Okay?
Okay, so hold on. Yes, EagleCAD schematic. Yeah. Okay. EagleCAD. So the way we do EagleCAD is I need to bring this over and open it because I'm a boomer who uses Linux. Oh, by the way, this runs on Apple, Linux, Windows, all of the good stuff. Hold on. Sorry. That being said, if you're running it on Linux, you might run into a really annoying bug where if you try to run it, it'll tell you that it can't run. If you run into that, just let me know because I know how to fix it, and then it'll be able to run. Fingers crossed. Okay, so this is beautiful EagleCAD. On Linux, it has a glitch where it opens up the PCB window, which it should not. But this is what you'll be greeted with upon opening EagleCAD.
Ignore this. We don't want it.
Yeah, ignore this part. We don't want it. What we're really interested in is creating a project, right? So we head over to File. Yeah, it's a little bit hard to read.
The bottommost tab, like with the triangle, it says project. So that's where your stuff is.
Wait, is it possible to lower the lights maybe?
Yeah, it is. Big brain. They're somewhere over there. Okay, you know what? It's going to probably be a hell of a lot easier if I can see what I'm doing.
Ooh. Ooh. Ooh.
Hold on, I'm going to mirror my display so I can actually see what I'm talking about.
Does this help at all?
Yeah.
What about those ones?
Those ones? I don't know what they do. Let's see.
Okay, so you guys are going to
Oh.
have slightly lower
Oh, yeah,
resolution,
that's
but at least I'm going to be able to see what I'm doing.
Wait.
So what you do is you head over to File, New, Project. That's pretty easy, right? Then we give our project a reasonable name, such as AP Lab, Lab 2, Schematic. So don't name it.
Wait, do lab like 2_1. Because we're gonna have like a part 2 of schematic.
Yeah, well, that's okay. That's
Oh, you can add it later.
yeah. This is just an example of what a reasonable title is. Okay. Now what I did was I went File, New, Schematic, which adds a schematic, which I'm just going to immediately save as AP Lab 2 Schematic. But if you guys are wondering, I'm completely guilty of naming stuff stupid things myself. That doesn't mean that you should do it either. So right here, what you see is an empty white screen, right? If you want to add something to the screen, the way you would do it is by typing in add. As you can see in the top search bar, it typed in add when I typed in add. Then we just hit enter. What this will do is hopefully load all of the libraries that are available to you by default in EagleCAD. So for example, if you want to look at connectors, you would go into one of the connector libraries. That's kind of hard to do, so we can search for stuff. The way you search for stuff in EagleCAD, in my opinion, is really stupid. Okay, you can search for an exact string by going like this. So
The
if
search
you
sucks, by the way. I actually agree with Alexia.
see, it says sorry you don't match, which doesn't make sense. There must be a bunch of 0603 capacitors in here somewhere. Where are they hiding them? That's because you have to surround your search terms in asterisks. Why? Don't ask me.
There are a bunch of like search tricks with like underscores and ampersand, like every symbol you could ever think of that filter out specific sections. Okay, the search I suck.
Yeah, the search is stupid. Put
Also,
asterisks.
wait, as a note, if you don't want to type add every time, there's a symbol on the left that should be there for add. Wait, do you always use that?
I always just type the commands because that's
Oh.
faster.
I always click the like this. If you just click this, it'll open up the same.
Yeah, well, it's easier to type in add than remember where that is. So then we head over to, like, we want an 0603 capacitor. This library is called RCL. What does RCL stand for? Resistor, capacitor, inductor. So in the RCL library,
Hey, inductor doesn't start with an L.
yeah, I know it doesn't. Then we find the part. We can see its schematic representation, which is what we care about for the moment. We can also see its footprint shape. We don't really care about the footprint shape. That becomes relevant when we're going to start doing schematic.
As long as it's 0603, that determines the footprint as well.
Yes. So then we hit OK. Now, what this does is all of a sudden I have a capacitor right here, which I can plop down.
Whoa.
And then I have to hit escape twice. So right now you have a capacitor. You can zoom in on it. Looks really nice. But what value is this capacitor? Well, I don't know. Let's type in value. Okay, now when we hit value and then we hit enter, we can click the capacitor on this. This is another thing I hate about Eagle. You have to click
You have
on
to
the
click the
cross.
like that plus. Every component has a plus. Sometimes it's hidden in a haystack. So
Yes, so you hit on this, and now you can type in a new value for C1. What's the value you guys want?
100 nanofarads.
Okay, Tim, you're not allowed to speak anymore.
That's
Okay,
what I
Also,
now,
also, okay, wait, one more. Alexi's using boomer tactics. Add whatever like value. Those are all over here as well. So there's an add part, and there should be a value. One other way to do it is if you right click on the cross. Try right clicking on the cross.
oh my goodness.
Okay, it'll say all of this stuff. There's something called properties at the very bottom. If you open that, it'll show like, boom, you can change the name, position if you want, and then values over here, and then everything, anything else you want.
Yeah, okay, so that's another way of doing it.
Multiple ways to do the same thing.
Okay, pretty much so far right now we've covered add, the fact that you can drop it somewhere, and then you can change its value. That's not very interesting in my opinion. What if we wanted, hold on, let's add resistor. And I use the European symbols because that's what I'm used to. So it doesn't look like a squiggly line. So if you want to rotate this part because it's in the wrong orientation, which button do you guys think you hit?
R.
No, you don't. You hit right
Well, that's
click.
explaining Eagle right now.
Because Eagle was made by people with no common sense. You had to right click to rotate stuff. But then we place it down, we have hit escape twice again. Then we change this value, which I'm going to do the boomer way. Again, we have to click the cross, which is annoying, and we're going to make it 1. So just a little bit of at least how I do stuff. For resistors, I don't type in ohm afterwards. For capacitors and inductors, I use either F or H in order to be able to tell stuff apart. For resistors, there's no ohm symbol, so I just leave it blank.
Oh, if you wanted to do like, oh, nano or like thousands, you just write K or N after it. Like if you want 10K ohm resistor, you just write 10K.
Yeah.
You don't have to write down 10,000.
So right now I have 2 things, and one of the things about Tinkercad that I'm sure you guys all absolutely love was how to connect things with wires, which is perfectly designed in that program. So in here, you would use, hold on, I need to make sure I'm using this correctly. You type in wire in the top. Okay?
Or alternatively, you click the green corner, like the 90 degrees in the left.
And all of a sudden, what's this? You click on the end of one of your components, and all of a sudden you have a wire. Okay? And the wire is pretty smart. Oh no, it's not. You hit escape to end the wire after clicking it.
You can either click escape or click on the same point twice.
That's what I tried doing, and it didn't really work. But I was probably double clicking it wrong. So now what we have is a connected circuit, right? So what the wire does is it is where the electrical connection is in this circuit. Pretty much it means that this point right here is connected to this point right here through this green thing. Okay? It's not an actual wire in the sense that it is a wire. It's just a way for you to visualize the connection between components. Actual wires are called traces, and you have to get into them when you're doing PCB design. Let's say I don't want this. I just click on it, I hit delete. Click on it, hit delete. I'm going to show you how else to connect things, okay? Let's say we have something going on here, which I don't know what it is, but we can't just draw a wire from there. What we do, we go, we talked about this. Remember, for your MPU, and for your IMU, and for your radio, you're going to want to use labels. So what do? You type in label. Tim is going to say what else you can do to get it.
Oh, yes. All right. You type in label or you click. Ah. The one that looks like a label.
Right, so you click label.
It's like the guy who never uses the keyboard.
He types everything. What do you mind?
No, but you're a boomer.
You're the boomer. I click the button. There's like a million buttons on the left hand side. You think they do that just so like visual appearance? Nah, you click it.
No, they do it so that people like you can use the program. So what you do is have a label. You left click it. Hold on. You have to left click on a wire.
Oh yes, sorry. Labels label wires, by the way. Not like
Yeah. So you see that it says $1. What does that mean? First of all, I put
net one. That's what it is.
First of all, I put this in the wrong place. Let's add a little bit of wire here.
So in order to connect it to a okay. You know what? Let's see. I'm starting to see your point now. Eagle is not that cool.
Yeah, it isn't. Okay, so we go back to label. Okay, we add a label to this wire.
And you can add it, and you right click to rotate it.
Yeah, you have right click to rotate it, but we're not going to rotate it. Okay, so this wire is labeled $3. Okay, then we add another label to this wire. Okay, and we're going to label it $2. Now these labels are pre-generated for us. They don't tell me a thing, so I'm going to go to value again. Okay, now you have to go to the cross, click on the
properties. Boom.
Properties. Okay, so
and then name.
So we're going to rename this to something unreasonable. Okay, we're going to rename it to cool. Okay, so this one is cool. This one's $3. We don't want it to be $3. We're going to rename it to cool as well. So what do you guys think is going to happen when I rename both of them to cool?
Net.
Wait, who said that? Kia?
Yeah.
Okay. So when you do that, it's actually going to tell you it already exists.
Oh god.
Uh-oh. We can't do it through properties window. We actually have to go type in name, which I don't know why we couldn't just use value. We click name, we click on this. Now we can change the name to cool. Now what do you guys think is going to happen? It's going to give us a warning saying connect $3 and cool. So now what this means is if we zoom out, there's no direct connection from here to here, right? Like this is a direct connection. There's no direct connection here. That being said, because they're named the same thing, this will be connected to that. So these are very nice for when you have to organize stuff to make sure that there's not a whole spaghetti mess of overlapping wires, which there was in Tinkercad. You can just name stuff, which is really convenient, because then you don't have to worry about overlapping wires and you can organize stuff very efficiently. In fact, the next thing I'm going to do is I'm going to walk you through. Oh, yes.
One non-boomer note. Oh shoot! Wait, I just unselected it. Wait, type name again.
Oh man.
You'll see a button that's highlighted. That is the button you click if you want to name something. Also, wait, do you always do like this? Like the labels? I usually put it on the end, and then I rotate it to in this case it would go down, so that it looks like, it's like a connection.
Yeah, you could do it that way, but
Visual here. Okay. Also, what you were saying about them being automatically connected, yeah, it doesn't show it here. When we transfer onto PCB design, that is when you'll see the actual connection appear. So here is yeah, they're connected, but you can't see it. When you go to PCB, you'll actually be able to see it.
okay, well the move command doesn't work like how I expected. So this is all fine and good, but let's say you want to add the TPS 63001, which is the voltage regulator I talked about before, and I'm going to give you a quick rundown of how to use. Okay, we get rid of my email. We go to DigiKey. Okay, I kind of like DigiKey for looking at footprints because they have better footprint selection. We type in TPS 63001. Okay. We head over here. We see that there's 0 in stock, but that's not going to stop me because that means that it's going to stop you, which means I can safely do this. So all the way down here, you're going to notice under Documents and Media, EDA/CAD models by Snap EDA and UltraLibrarian. What this means is that some kind soul out there created this footprint for us so we don't have to suffer through Eagle's horrible footprint creation manager. Okay? So I like using UltraLibrarian. We go to UltraLibrarian, it is going to load. We can see the footprint right here. We can see the schematic symbol right here. We can see the 3D model right here. I don't care about the 3D model. Some of you might, I don't know. But the point is, we can go click download now, log into download. You do need to create an account, but they don't ask for credit card information or anything.
Most of these aren't crazy sus. They're okay to use. I think Snap EDA, Snap EDA is good. And then we link more in the lab, yeah. If you can't, Alexis having it. If you can't find one on DigiKey itself, just go on the individual websites and then search for the part. Almost all the time, you'll see something like that.
Right, so here's another reason I hate Eagle. So Eagle is made by Autodesk, okay? Now which one of these 4 formats do you think you want to pick to download the part correctly?
KX4TD.
You actually want to use Eagle 6 library, but still the fact that there are 4 separate formats is kind of off-putting. So what you would do is you'd click download now. It says view tutorials. I guess you can click on that. I have no clue where that goes. And then it says, wow, check it out. You can download this as a .zip file. So when we go open this, show in folder, it is going to be this zip file we just extract here. There's nothing fancy. If we open this, what we're going to find is inside we have, God damn it. Okay, well we're going to pretend we downloaded the one that I downloaded earlier, which I actually verified works. We're going to notice the .lbr file. The .lbr file is the library file that Eagle recognizes as the part. So now that we downloaded this correct one, what we're going to do is we're going to head over to, where's Eagle?
Well, this is what you're going to have to do for probably the more specific parts that you have. Resistors, capacitors, inductors are in the RTO library almost all the time. And this is as he's explaining with the voltage regulator, you might have to search for the voltage regulator. And the library is a general mapping package, and then inside the library there's parts. But in these libraries, there's just going to be 1 part per library because it's the part library.
Right, so if you want to add a part to your libraries, you right click on libraries, you open Library Manager, you wait for it to load a little bit, and this is going to take a little bit because my computer.
Oh, also, you can also look at Library and Library Manager from the schematic page. It should be at the top of like file or whatever bars. There will be an option for a Library Manager, I think, in either file or editors or tools.
Right. So right here, if I want to add something, I hit Browse. I go to, I don't remember where I saved it. I think it was in Eagle. I see it. Right. So you see it pops up the .lbr file. We hit Open on this, and you see how this part just popped into my list of libraries. So I don't have to hit Save or anything. I just hit Close. And now when I head over to my actual schematic and type in Add, we can see right here, I don't even need to search for it. Here's the TPS 63001 that we downloaded from DigiKey.
If it's lost in like this ocean of libraries, a really easy way to see is just that you can see everything else has an Eagle PCB labeled right after the name, and this one doesn't. So that just means it's like a custom file. Yeah.
Right, well we hit Add. Okay, we've got our beautiful voltage regulator here, the TPS 63001 VRCT. It has 10 pins on it. Well, it has 11 pins. What the hell do these pins do? Okay, I mean obviously ground is connected to ground, V out is like the output. The rest, who knows? So what we do is we head over here. This is the TPS 63001. We click on this scary file called the datasheet. Now when we open up the datasheet, it's going to take you to a PDF document which surprisingly describes the entirety of the chip's operations. So remember how I said we want a chip that can take in 2.3 to 5.5 volts? This one can take in 1.8 to 5.5, that's good. 96% efficient, that's good. 1.2 amp output current, good. Looks pretty good, right? Except it's out of stock. Which is why I'm using it, because you guys can't copy me. So right here, we can see a typical application schematic. Typical application schematic shows how you should implement this circuit in your design. That being said, this is also a bit misleading because a lot of voltage regulators lump all four of these. You can see 000, 001, and 002 are all on the same data sheet. This is specifically for the 001, as you can see down here maybe. It's a kind of low-res screen. But this is only true for the 001. You can find the other ones later in the data sheet by going here, and you can see pin configuration and functions, detailed description, application, and implementation. Then we go to typical application, detailed design procedure, I believe, and we don't actually go there. We go to layout guidelines. No, we don't. Hold on. So where do we go? Application implementation. Right. So here's typical typical application for TPS 6300X circuit.
X is variable.
X is variable, but in this specific case, I can tell you it's a 000 because it has this voltage divider right here. You're going to need to read the data sheet to figure out which one this one's referring to, okay? So reading data sheets is important. Fortunately, for most of them, they actually properly label them which one it is. In this case, they didn't. Bad on them.
The idea is you're going to copy paste this into your schematic. Of course, it's not copy paste. You're going to have to put capacitor where C1 is, resistor where R3 is, L1 conductor, so on. And then make those connections yourself, but copy paste that design.
Right, and actually that's exactly what I'm going to walk through you guys right now. Because this is going to be a good lesson in how to connect things. Like, it's going to be a good review of all the other commands. So I just showed you how to import stuff just by adding stuff.
Also, as a general note for voltage regulators, VIN, they always say in the data sheets, but just to clarify, VIN is what we're inputting. So that's going to be our battery, our 3.7 volt battery. Vout is going to be what we're putting into our MC. So that's going to be the 3.3 that we want. And it says it here, so it's perfect.
Yeah, so let's see, what's the first thing you see? L1 and L2 are connected to a 2.2 microhenry inductor. This is the symbol for an inductor. So we're going to go add, okay? We're going to go, okay.
Can you search RCL?
You can search RCL, no you can't. We're going to search,
when in doubt, just use asterisk.
Yeah, asterisk. So, even though it's an RCL, hold on. Mamma mia, this is why people go. So we go,
Oh, no.
oh my goodness. Okay,
I think usually when I do it, I just take the long way around, just scroll down to RCL.
yeah, in a reasonably designed program.
There has to be a better way to do it, but I
Yeah,
don't know.
use KeyCAD. So then we go to Industrial European, okay? And you see the packages here are like 0204, 0207, blah, blah, blah. We don't really care about that for now,
So we're on
so
603, because I think we saved it.
we don't have an 0603, buddy. It's just 0204. Right, let's check the American library. Maybe they have it in American unit.
You can use whichever one you want. I think I used US, but it isn't.
Right, well, they don't have it in America, in correct
Okay,
units
then you have
here.
to import it. Basically, you can just search it up. But we won't go through that.
But the point is, this is what an inductor symbol looks like. So we put it down, and if we remember correctly, oh, it's connected to L1 and L2. So we go wire, click on this end. That's really ugly, I'm going to fix that later. Yeah, I'm not an artist. Then we drop it down here, right? So we connected those pins, that's good. Let's really quickly delete this because it's an eyesore. Okay, so that's one thing done. And it's 2.2 microhenry, so we go value, we click on it, and then we type in 2.2 microhenry. I use the U symbol for micro.
Oh, by the way, every single gray label you see here, like the 2.2 microhenry or like the L1, you can see there's a little gray cross. And that's just like, the cross is always where you select what you're looking at. So the gray ones are going to represent the labels. So if you want to click and drag those around, you can move them to wherever you want them to be.
Well, Tim says you can click and drag them around, but if you click them, they don't do anything.
Oh, that's because you have to.
Yeah, I know you have to, but I'm just saying that you're lying. Okay, so we can see that we have 4 capacitors here, so we're going to go add, and we're going to type, this time we're going to do 0603 because those actually exist. I'm going to use again the European capacitors because I think they look nicer.
What do you use in European and American?
Just the, oh yeah, I mean, I'm looking at the wrong one. So the American ones have like a curved bottom plate.
Oh.
I think that these look cooler, so I use these. There's no difference really.
Yeah.
So if you remember, we had 4 of them, so 1, 2, 3.
And what Alexa's doing here is really smart. Just make sure you read how many you need and just boom, 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 so you don't have to keep reopening and closing.
Right, and then looking at this, well, it's 10 microfarads. Okay, what we're going to do is we're going to find this little cross here, which is hidden. Click it, type in 10 microfarads. We're going to look at this one, 0.1 microfarads. We're going to again click this block, blah, blah, blah.
This is very smart as well. Just value all of them before you start wiring them up, so that after all your components are on, then you start wiring, and then it makes it a lot easier. Or it saves time at least. Also, while he's doing this stuff, all of the all of the choices for mouse, different types of mouse selections are at the top left. Like the double arrow one is for move. Like if you select that and then you click on any part, it'll you can click and move them around. And same with the labels. That will be the one that allows you to do labels. And then the other one, like with the box and the mouse, is just the classic select. Basically, that's just like a normal.
Yeah. So then continuing, we see we have 1 resistor here, which is going to be 100 ohms. So we go add, and then wow, check it out. We're going to type in 0603. I'm going to use the European symbols, and again, that's just the way I do. Then we have to right click to rotate it, because obviously. Then we put it here, and we check the value. It's 100 ohms. So we type in value. We put the cross in a nice place here. So we just type in 100. Okay, we pretty much have everything we need. So let's start wiring it up. So we can see that these 3 pins are connected to each other and they go into the capacitor. So let's do those first. So that's going to be what? PS sync, it's going to be this. Okay, let's go out 1. And V and A. And they're connected like this. And, hold on, is the junction not going correctly? Okay, well that's another reason. Oh no, it looks like it did. So then we go move. We move this off because remember it's on. No, we're going to move this over actually because otherwise it's going to be ugly. That's unacceptable. Right. We're going to move this here. We're going to move that down. We're going to move this off because remember V in goes along the top of these. See right here, V in. It's above the resistor. So we're going to go. Okay, we're just going to implement this. But this is really ugly. You guys can make it as pretty as you want, but you know. Yeah. So then we add a wire here because it's connected. Then we go ahead and move this. And this is just me literally copying the schematic. Unfortunately, although you can get the footprint, no one really pre-makes these circuits for you, which kind of sucks. I wish they did. That would make my life a little bit easier. And why would it make my life harder? Oh, yeah. That's the only reason that we're doing this actually. Here we can see that feedback, that's what FB stands for, it's not Facebook. It's connected to V out. So let's do that. We're going to move this up here. It's connected to V out. And V out goes all the way out here. So we're going to go all the way out here too. Damn it. I'm sorry, I'm using keypad shortcuts. Keypad shortcuts. So then we move these capacitors because if you remember, they're just hanging off this thing. So it'd be probably reasonable to move them here.
Yeah, there we go. That junctions will be shown by dots. I don't know what that is.
We'll look at that a bit later, actually. And then we have ground, or P ground, ground, and PP. So you might be wondering, what does PP stand for? And since you're no longer in elementary school, you're not laughing at it.
Right.
It stands for, it's going to be the bottom of the thing. I don't know what it's called.
That's the high risk. Okay, that's the leap of faith.
Yeah, that's the leap of faith. Pretty much the footprint of a V-SON.
Well, no, but the good news is, in this case, the PP isn't connected to anything.
Okay, so this is the PP, okay?
Dude, everything has it, I swear.
Yeah. Hold on, maybe it says what it actually is. No, it doesn't say what it actually is.
I don't think it's connected.
No, it's connected to ground. PP is usually connected to ground. So we're just gonna draw off this here.
So that's a normal case. Like the bottom, there will be a plate on the bottom that you can't visually see from the outside if you set it down on your PCB, and that's usually connected to ground. For what reason? Heat dissipation.
It is heat dissipation, and you generally want a good connection to ground with these circuits anyways. So we're gonna re-zoom back on this thing. So you have these weird inverted pyramids everywhere. That's a symbol for ground. So we just want to connect the bottom of the capacitors, ground to ground, and just bottom of capacitors in general. So we're going to go and add.
There's a symbol for ground. You don't have to search it up or like make drawing or whatever.
Well, check it out. It's a symbol for ground. Actually, this isn't the one I want to use. I want to use this one because this one looks cooler. So this is a symbol for ground. We can just attach it to the places where we want ground to be attached to. And it's going to ask you, do you want to rename this net segment N6 by supply pin ground? When you apply this, it applies a name to your net so that everything named ground will be connected to ground. We want this, so we're going to click yes.
This is like a label that they give you because everyone uses ground.
Yes. And then the other thing we have is we have, so our input is going to be, well, our output is going to be 3V3. So check it out. We have an output symbol as well, which we can put right here. Then we can wire this bad boy up. Yes, we
Same
want.
idea. This is like these are all power supply labels, so it's just like a label, but they give it you.
Okay. And then our input voltage is going to be variable. But that being said, we can safely assume that it's going to be 5 volts, or less than 5 volts. So we're going to type in.
What is it like VDD or
Oh yeah, they have a symbol for that as well. CVD. So then we go supply. This one's really ugly, so we're going to go with that one because that looks cool.
As long as you keep it consistent, it'll be fine. And also, you can just choose to use your own labels first, but I think it's a lot easier to use their predetermined ones.
Right, and then of course we want to merge net segment $N4 and supply net VDD. So what we did right here is we implemented the typical application schematic of this part, which we imported into Eagle, in Eagle. And yes, it looks a bit ugly, but it also looks correct, which is more important than it looking pretty. We added the labels here, so anything that's connected to another 3D3 arrow will be connected to this, which is what we want. If we connect the battery to VDD, these two will be connected. We have a resistor, we have all the capacitors that they asked for us. We connected these 3 pins to ground, which is important, because otherwise it won't work. It works, or it should work, in theory. Pretty much, oh yes, Tim?
Yeah, about what he was saying, like connecting VDD to battery. You will be having a battery in your schematic, and there will be a connection from the positive terminal of the battery to a couple other stuff to another label. We can call these labels, but like there's these symbols for VDD, and then if you connect the positive terminal of the battery to the symbol VDD, it will automatically be connected. Same idea as labels.
Right. So what we did here is we pretty much did one of the parts of the schematic for you. Except we did it with a part that you cannot feasibly use. So we didn't really do anything for you besides the demonstration. That being said, I want to ask, are there any questions? Yes, so it is a strange convention. I have a feeling that it exists because early programs wouldn't allow you to put periods in between things because that'd be like special character. You also sometimes see this with resistors where it's like 3.3 came as like 3K3 or something dumb like that. But 3V3 is just one of those holdover like standards where it used to be like this and everyone does it now. But yes, it's 3.3 volts. That's how you read it.
Other questions?
I know this is a lot to take in, but trust me, it makes sense. It's like MS Paint, but easier. Because like all this stuff is pre-drawn for you and just draw the lines.
Wait, so it's horrible?
Yes, it's Eagle. Of course it's horrible. Was there a doubt about that? The fact that, like, someone said R to rotate, but no, it's right click. Okay?
R stands for right click.
R does not stand for right click.
There's a bunch of tutorials online, and if you have any questions about, oh, how do I don't know, let's say you forget that it's not R, because apparently you'll suck. Let's say you forget how to rotate the thing. Search online, that's it. And then we're linking up the tutorial and all that.
Yeah, that being said, there are a lot more EagleCAD tutorials out there.
Final questions.
Are there any final questions?